Welcome to ChemExam Explained, where the aim is chemistry clarity, exam mastery. In today's video, we will be looking at CSEC Chemistry, May-June 2011, question 2. Let's go. 2A. Depending on their structures and properties, solids may be classified as having metallic, giant covalent, simple molecular, or ionic lattice structures. The structure and conductivity of selected solids are to be summarized in Table 3. Part A. Complete Table 3 to show the structure and conductivity of each solid substance listed. The first one is done as an example. So here we have magnesium chloride. Its structure is ionic and conducts electricity in the solid state. That would be a no, because the ions are not free to move or flow. So let's complete the structure for the others and whether they conduct current or not. Iodine is a simple molecular structure, and iodine does not conduct electricity in the solid state, right? Or the molten state or liquid state. But in this case, we're looking at the solid state, so no. Zinc is metallic in structure. You could say giant metallic, and it does conduct in the solid state due to the delocalized electrons present in the lattice. Diamond is a giant covalent structure and does not conduct electricity in the solid state. 2B Part 1. Magnesium chloride and potassium nitrate have ionic lattice structures. Figure 2 on page 9 shows the solubility curves for magnesium chloride and potassium nitrate. Use the information in Figure 2 to answer the question below. Part 1. Which of the two compounds, magnesium chloride or potassium nitrate, has the greater solubility at 15 degrees Celsius? So the first thing we want to do is to find the temperature, 15 degrees Celsius, and it is right here. We are then going to be looking at that value for potassium nitrate and compare it with the value for magnesium chloride. And you'll see that magnesium chloride would dissolve a greater mass of salt in 100 grams of water than the potassium nitrate. Therefore, magnesium chloride would have the higher solubility at 15 degrees Celsius. 2B Part 2. Calculate the mass of potassium nitrate that would be deposited when its saturated solution is cooled from 80 degrees Celsius to 20 degrees Celsius. So what we're going to do is to look on the graph and find potassium nitrate. And so this is potassium nitrate. We're then going to find our temperatures of 80 degrees Celsius and 20 degrees Celsius. We're going to interpolate from the x-axis to touch the potassium nitrate curve, and then we're going to interpolate across to find the value, which is the solubility of potassium nitrate at 80 degrees Celsius. And that value is 14.4 grams. We're going to do the same thing for our 20 degrees Celsius. And when we interpolate and go across, we find our value to be 7.6 grams. We're now going to subtract by saying 14.4 grams minus 7.6 grams to get a value of 6.8 grams. So that would be the mass of potassium nitrate that would be deposited when the saturated solution cooled from 80 degrees Celsius to 20 degrees Celsius. 2B Part 3. Determine the temperature at which the solubilities of magnesium chloride and potassium nitrate are equal. So let's go to the graph, and you'll see that we have our potassium nitrate curve here, and we have magnesium nitrate here, and they intersect at this point. And this is the point at which both potassium nitrate and magnesium chloride would have equal solubility. And so we simply find that value in terms of its temperature, and that would be 56.5 degrees Celsius. So that would be the temperature at which both the solubilities of magnesium chloride and the potassium nitrate are equal. 2C. Draw the bonding diagram to show how magnesium combines with chlorine to form magnesium chloride. So what we're going to do is show you how we move from magnesium, which has 282, so I'll just use the valence electrons on magnesium. So this is magnesium, and I'm showing only the valence electrons. Now I need 2 chlorine atoms, each containing 7 electrons on its valence shell. In order for magnesium to become stable, it must lose its 2 valence electrons. So one will go to one of the chlorine atom and the other to the other chlorine atom. Now, here I have 282. This is 287, 287. But now, losing the last 2 electrons, I now have 1, 2, 3, 4, 5, 6, 7, 8 electrons on my valence shell. So I no longer have this outer 2 electron there. So it is 2, 8. And now this is no longer magnesium atom, but magnesium ion. So Mg2+. What I should have done was to draw the box around it and then put 2+ here. And now I have Cl- because this had 7 electrons, all right, and it acquired 1 electron there. So now this is Cl-, and the other one would do the same, and that is Cl-, and this will give us the formula MgCl2. And that is how we move from magnesium atom reacting with chlorine to form magnesium chloride. Now you see here I have 2 in front of the Cl- because instead of drawing 2 of the Cl- ions, you could draw 1 but put 2 in front. Now either way is correct. 2D. Based on the use and purpose of solid air fresheners, would you classify them as having simple molecular, giant covalent, or ionic lattices? Explain your answer. So we would classify them as simple molecular. This allows them to diffuse easily into the air by breaking the weak intermolecular forces found in simple molecular solids. That is, simple molecular bonds are easily broken to release scent. Giant covalent and ionic lattices are strong bonds and cannot be broken as easily as that of simple molecular bonds. This is the end of CSEC Chemistry, May-June 2011, number 2. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.